moment capacity is based on what we call the plastic moment capacity. Okay, instead of using the section modulus, elastic section modulus, maybe you saw this in an earlier session, S, which is I over C. Okay, typically we don't use that now in LRFD. Instead, we use what's called the plastic section modulus, or Z. And Z sub x meaning it's the section modulus about the x-axis. Now what we do is we take that, multiply it by Fy times 0.9, and what that does is it gives us the maximum moment capacity of the beam. Okay, what the plastic section modulus does is it gives us the capacity based on a fully yielded cross-section, meaning that we've reached Fy everywhere on the cross-section, because it's not until then that we've actually reached the maximum capacity of the cross-section and we'll get failure. Okay, even though we may yield on the cross-section, the member won't fail until it yields all the way through the cross-section. Okay, and that yielding through the full cross-section is given by the Z, or plastic section modulus. However, what actually happens is that we try to reach what we call MP, or phi M sub P, if we put in the 0.9. The problem is, if we're susceptible to other failures, such as lateral torsional buckling, we may fail prior to that. So what happens is we may be designing to a reduced moment capacity that's somewhere down in here. And we'll see their design equations depending upon whether we're in one of the three regions here, which in tabular design you don't really have to worry about. Like with a column, we also have to worry about local buckling. We have to check slenderness of the flange and web. We use the same slenderness ratio as we use for a column, but now the limits are a little different. Instead of 95, it's 65 for the flange, and instead of 253 for the web, it's 640 for the web, and that's just because the stress distribution is different in a beam than it is in a column. Most of the W shapes that you find in the manual don't have problems with local buckling. Okay, in fact, I don't know if any of the columns have problems with local buckling. Just a handful of the W shapes have problems with local buckling and bending. Thing is, if you manufactured a shape that had problems with local buckling, no one would buy it. Okay, because you end up having to reduce its strength, so they just don't manufacture them. Okay, again, we said that the maximum moment capacity of a beam is based on the plastic section modulus, or it's defined by phi M sub P, or the plastic moment. The problem with beams is that there may be an evil force lurking that will reduce the capacity, and that evil force is lateral torsional buckling. Okay, what will happen is, if we don't properly brace the beam, as the bending stress increases, the compression flange, say here at the top, increases, and because the stress in here is compression, at some point, if the stress gets high enough, it behaves like a column, and it will buckle laterally, like so. And as it buckles out, it pulls the whole cross section with it. It twists around, and the load kind of slides off, and you get failure. Okay, so we've got to guard against lateral torsional buckling. Now, we can measure that by a slenderness ratio. We don't really use this, but it's the unbraced length divided by the radius of duration about the weak axis. Okay, so one way to prevent lateral torsional buckling is to provide bracing of the compression flange, and a lot of times you get that just by the way you construct the building or the frame or the system, what have you. A floor slab will give you that, provided that the concrete floor slab is somehow attached into the beam, because that will prevent the lateral buckling. Also, we'll get bracing at intermediate supports. If we have other beams coming in at right angles at certain intervals, well, then that will prevent this type of motion. Okay, in this case, our unbraced length, okay, or the distance between the bracing points is actually 0 because it's continuous. However, if we come in and if we look down on it, if we have our beam and then we got another beam coming in here, and then we come over here and another beam is down here, then what we have is an unbraced length that's defined by the distance between the bracing points. Okay. What happens is, as the unbraced length increases, it's like increasing the length of a column. Okay, so as your unbraced length increases, you become more susceptible to lateral torsional buckling. When you get into the design, you're going to have to limit your moment capacity more as the unbraced length increases to prevent this type of failure. Okay, the nominal moment capacity, M sub n, which is just the design capacity without the phi factor, okay, is given by the following sets of equations. You don't really have to worry too much about these because they have what are called beam charts that you can use for design. But now, if our unbraced length is less than a value or a length that we call L sub p, then we don't have problems with lateral torsional buckling. You have to get up to a certain unbraced length before you begin to have problems with lateral torsional buckling. However, if you cross that threshold with your unbraced length, then you have to start reducing your moment capacity to prevent lateral torsional buckling. And you actually, for this equation, you have two upper and lower limit. When L sub b, or the unbraced length, is between LP and LR, then the moment capacity is given by this. When you get over that, again, it's acting like a long, slender column. Then you have to reduce the moment capacity even further, and it's defined by this equation. Okay, those equations that I showed you were developed based on a moment diagram in the beam being constant along the length of the beam. Pardon?
What are LP and LR?
Okay, LP is the maximum unbraced length that you can have and still reach M sub p. Okay, meaning you don't. Okay, LR is just another limit that's defined. Okay, it actually is the limit at which you don't yield anywhere in the cross section.
Actually, it's the break point between the two equations.
Yeah, it's just a limit of the equations. It's the limit between this is actually called the inelastic region of behavior, and this is elastic behavior. If you were able to look at the stress distribution at the beam, in the beam, right at failure, you would come in and notice that nowhere is there any yielding. You have a linear stress distribution.
At L sub r?
No, below L sub r.
Okay, longer than L sub r.
Or up to L sub r. If you got into this region and drew the stress distribution at failure, you would find that at the extreme fibers you had reached Fy. But as you got towards the neutral axis, you go back into the elastic region. Okay. Really, these limits, LP and LR, are defined just to define which equation to use.
And when you say we're not going to use the equation anyway because you're going to use the beam charts.
For the purposes of this exam and quick designs, you don't need that anyways, because the beam charts incorporate all this. Okay, on that note, why don't you can digest that a little bit. If you still don't, still have a question with that, we can come back. But let's break for 5 minutes, just to get up and get the blood flowing again.
Gary, I was going to ask you something, too. Know what she was asking? You know, what would be good, well, to put in that table, circle the 23 feet, circle the, you know, and show the intersection.
Yeah, I know.
Circle across and shoot up so that you pull that thing out of there. So the guy didn't show up to hitch up our good stuff.
I think they're trying to get me to work late tomorrow night, too. He called me about 8 o'clock this morning and said, well, the guy hasn't been able to leave yet. How late are you there Fridays?
Fridays, nice guy. Oh, well, I normally go till 9 or 10 at night, huh? Sure you do.
Pardon?